My name is Matthew McKnight. I am a programming mentor for Team 4536, the Minutebots, and I'm here to go over some of the current structure in FRC command-based programming for this year. So we're going to look over the basic file structure that it's using, and we'll also delve a little bit into what command groups are and how they can be leveraged to make your robot much more powerful. Now, the command-based programming structure consists of four main files: main.java, robot.java, robotcontainer.java, and constant.java, all located in the FRC robot folder. There are also two subfolders, commands and subsystems, which are where you will store your files for the subsystems you're going to create and the complex commands you're going to create. So the first thing we should do is look at the four main files to understand what their purpose is, what their concern is. Main.java is kind of like a visitor center. I've recently gone to a few colleges with my children to look at them, to take a tour of the college, see what we think, and we always start at the visitor center. If you don't know where to start when you're going to tour a college, you always start at the visitor center. Main.java is very similar. Java needs to know where to start the program. There's a lot of different files it can look to. So what it does by default is it looks at main.java. And within the main.java program, it uses the static method called main. Before we go on, I want to look at a couple things in this method which will be useful going forward if you come across them in other code. They're basically there to make writing code easier and cleaner. You will probably not use them in writing your own code, at least initially, but if you come across them in other code, you should be able to recognize what they do. So the first one is the parameters string.args. Strings followed by ellipses, args being the parameter name. When you throw in ellipses after a parameter type that's going to be passed in this case strings, it is what is known as a var args. In other words, a variable argument. And what that means is that the number of parameters that can be passed in varies. You could pass 0 parameters, 0 strings in this case, or you could pass 100 strings if that's what you wanted to do. This could be useful, for example, if you're setting up a drivetrain and you don't know at the onset how many motors you're going to use. You could use the ellipses, motors ... to enable you to pass in as many motors as you wanted to create the drivetrain, rather than overloading it multiple times. This is similar to an auto overload. So rather than write multiple overloads for whether you pass 1, 2, 3, 4, 5, or 6 motors, for example, you could simply say motors ... and that would tell it that you want to put in a variable amount of motors into the method. So for example, if I have a method called setColors, string ... colors, I could call it as setColors, or I could call it as setColors with 1 string variable, or I could call it as setColors with 2 string variables. I could call setColors with 6 string variables. I can even pass in a variable which is an array of string objects. Now it doesn't just have to be strings. You can create these var args with any object or primitive type. It just enables you some flexibility when you're creating a method where you do not know at the point at which it is being called how many parameters are going to be passed in. The second thing I just want to bring to your attention that is probably going to be new to you is the robot : new parameter that you see in the robot-base.start robot. The : is what's known as a method reference. What it really does is it simplifies code. So similar to lambdas, which we aren't going to talk about here, it simplifies the writing of code to make it cleaner and simpler if you understand, of course, how it functions. So in this case, robot : new means that you're going to call the new method on the robot class. So robot : new is the same as calling new robot. In this case, it really, as you can see, doesn't save a lot of space. But going forward, when you run across it, you will see that it can be leveraged very nicely to make code clean and simple and shorter. However, if you do not understand what it does, it can be very confusing. So I just want you to know, if you ever see this double colon, what it's actually doing is calling a method on that particular class. So just so that's in the back of your mind, so when you see it, you'll know that it actually means something. Going forward, robot.java can be thought of as the bus driver. The bus driver picks up the bus from the garage, and then it drives you to the stops, making sure that you're at where you need to be. The first thing the bus driver does, of course, is it picks up the bus, and this is in the robot init method. So as you can see in this robot init method, I've instantiated a robot container as a class level variable to be used within robot. Now there are a number of previously defined methods which you can override and which you will possibly want to override, some of which you won't. One of the most critical is robot periodic. In robot periodic, which you will probably not touch at all, you have command scheduler.getInstance.run. Now the get instance gets the current instance or the current object of command scheduler and then calls a run on it. So basically you're calling the static method getInstant to get the current command scheduler that already exists and then call run on it. Robot periodic will run approximately every 20 milliseconds. And what a command scheduler does is it looks to see what commands need to run, and then it runs them. So you will not touch this. This is just what the bus driver does to make sure that the command scheduler is running every 20 milliseconds. The override in teleop init is just an example of something else the bus driver does to make your life easier. The bus driver, or the robot focus, is to make sure that everything is running smoothly and you're where you need to be. And in this case, in the teleop init, when you're initializing the teleop mode, what it wants to do is make sure there are no autonomous commands running. So it looks to see if there's an autonomous command running, and if there is, it cancels it. So this is a means by which it makes sure that when you start the teleop mode, you're in teleop and no longer in autonomous. So again, that is the focus of robot. It instantiates the robot container, and then it makes sure that when you go from mode to mode to mode, everything is set up correctly. Robot container itself can be thought of as the bus mechanic or the bus garage. It puts the bus together for the bus driver. The robot container's concern, and it's similar to the robot in FTC, is it creates the subsystems, it creates the commands, and it assigns the commands that you want to the joystick buttons. Now it doesn't deal with the sticks, but it deals with the buttons. So for example, if you wanted a button to shoot the pellet, then you would assign it here in robot container. Its concern is the basic structure of the robot in commands and systems and button responses. The constants.java file is one you should be familiar with. It provides the specifications for the bus. So it's a central location for setting constants used to define the robot hardware and function. For example, if you want to assign the drive motor IDs, this is where you would put them. We leveraged this a little bit in FTC. We're going to leverage it heavily here because the more complex a program becomes, the more important it is to have a centralized location for information and to minimize hard coding of variables. If you have it here, it will be easy to change and quick. If you bury it in other code, it will be hard to find. So constants is a means by which a programming team in a complex structure can have some set understandings of what the variables are, and you can see quickly if there are issues. Now subsystems are really what we used in FTC as a combination of commands and subsystems. What subsystems do is they generate the hardware. Unlike in FTC where you're handed the hardware in the hardware map, here you are actually within the subsystem itself going to create and instantiate the hardware. That encapsulates and protects it from the rest of the code. In addition to instantiating the hardware, you're going to create the basic methods by which the hardware is interacted with. So in a drivetrain, that could be simply a drive method, or a go forward method, or a spin method, or some other method that you would use. There's two main things it does. It instantiates the hardware, and then it makes that hardware available through methods, encapsulating it, as we've talked about, protecting the actual hardware itself from being messed with. One other thing that's very important to understand about subsystem is that subsystems have a method called periodic. This method, periodic, runs whenever the command scheduler is called, about every 20 milliseconds. And this is very useful when you are in control of the hardware to update the information on the hardware. Now, it will not be used to make any changes to, let's say, the direction of the robot. What it does is it allows information to be available to the commands that are running the system. So if you have a gyroscope on your drivetrain, you could update the information that a command will need to know when it is deciding how to drive the drivetrain. You don't decide that in here. All this does is it uses periodic to update the information for the commands to use. Commands themselves, in the command subfile section, generally are going to be complex. There are some commands, specifically the run command, which you can use so that you don't have to create multiple files within the command for simple commands. So looking at the drive method, for example, you could create a new run command with that, and we'll see that going forward, how that is used. So the command files are actually used more often for complex commands, complex systems. A good parallel in FDC would be the autonomous op modes. So you have a series of commands being run, or a sequential series of commands being run to accomplish a particular task. For example, you want to drive your robot forward, spin up the shooter pellet, and when it gets to the right speed, you want to shoot the pellet. You would use a file in the command folder to give it that direction. We're going to look a little bit more into that so you can understand how that works. But there are four main types of command groups: the sequential command group, the parallel command group, the parallel race group, and the parallel deadline group. We're going to look at each of these so you can understand how they can be leveraged. Let's say we have three methods that we're going to use in our command file. The first is drive forward. That method is provided by the drivetrain subsystem. Spin up shooter, which spins up the shooter until it gets to the necessary speed that we need, and shoot ball, which actually launches the ball out of the shooter, are both found in the shooter subsystem. We're going to look initially at just drive forward and spin up shooter, so you can understand how these four different types of command groups work. And then we're actually going to combine them, because you can have command groups call command groups, so you can see how powerfully they can be used in your robot. So drive forward and spin up shooter are going to be used in the sequential command group, a parallel command group, a parallel race group, a parallel deadline group ending with drive forward, and a parallel deadline group ending with spin up shooter. The sequential command group is just like the FDC. It is what's called a single-threaded application. So in other words, you have one thread. And since you have only one thread, you can only do one thing at a time. You can either walk or you can chew gum, but you cannot walk and chew gum. If you do a sequential command group, you can drive forward, and when that command is done, you can run the spin-up shooter method in a different command. And when that command is done, then the sequential command group itself is done. So they are in order at which you put them as parameters into the sequential command group. When the final command is done, the sequential command group is done. The parallel command group, on the other hand, uses a multi-threaded system, and that means that it can do more than one thing at a time. It can walk and chew gum. So in this case, the drive forward, which is used by a command, and the spin-up shooter, which is used by a command, will run at the same time. And the parallel command group itself will end when the last command is finished. So in other words, it will go until every command is done. The parallel race group, on the other hand, is similar but different because it ends when the first command to complete is done. So they start at the same time. You're walking and you're chewing gum, but as soon as you stop chewing gum, or as soon as you stop walking, you stop the other as well. So as soon as the first command in the list is done, all the rest of them stop because the parallel race group stop. So in this case, even though drive forward isn't completed to where you want it to be, it will stop as a command. The parallel deadline group, as we see in the drive forward and the spin up shooter, are defined by the command that you say will end the command group. So in the top case, drive forward will end the command group, which means that the command group will continue until drive forward is done. The bottom one, where we've chosen spin up shooter, the parallel deadline group will end when the spin up shooter ends, regardless of where any other of the commands are. Now as we go forward, you'll begin to understand how each of these is leveraged, but I want to give you a quick example of how this is used in FRC. Now remember, we have the drive forward, the spin up shooter, and the shoot ball methods, all of which are going to be called by run command. And you'll see how that works. What we really want is the drive forward and the spin up shooter to run at the same time and then end when the last one is done. So we don't want it to end before the drive command has gotten into where we want to be, and we don't want it to end before the shooter is up to speed. So we're going to do a parallel command group for that one. And then when that is done, we want to shoot the ball. And so we're going to wrap that first parallel command group and the shoot ball in a sequential command group. And it will look something like this. Now notice that I can call a new run command, and all that does is simply call the method as a command. It will call the drive forward and the spin up shooter as a parallel command group, and when that is finished, it will run the shoot ball command. Now before we continue, there's one thing that is very important when you think about command groups and structuring them, and that is that you cannot have two commands that use the same subsystem. This is very important and makes a lot of sense because what you're going to do is confuse the robot. Let's say at the same time you chose drive forward, you also told it to spin as two separate commands, not as part of a sequential structure ever, but as two separate commands you told it to. A, I want you to drive forward, which means all the wheels are going in the same direction, and B, I want you to spin, in which case the right and left are going in opposite directions. The robot has no idea which one to do. We're not talking about doing a curvature drive or swerves. We're talking about two conflicting commands, both of which require the same subsystem. The robot will not do that because it makes no sense. So, if I remember correctly, it will actually choose the last one, but better than trying to make the robot make the choice, we have to make the choice. So it's very important in this case where spin up shooter and shoot ball both use the shooter subsystem, we would not call them in anything other than a sequential structure because the robot won't know which of them to obey. So that's just something to understand as we go forward, and you'll understand that as we develop the drivetrain subsystem and a drivetrain command, how that will work. But subsystems can only be controlled by one command at a time. So I know this may be a little bit of a fire hose and overwhelming, but I wanted you to get sort of a quick overview of the structure to stick in your back of your mind, so as we develop the drivetrain, it'll become more obvious how each of the pieces work. So the next step for us will actually be to develop a drivetrain subsystem and to develop an autonomous command, which will then use that subsystem going forward. We'll see you in the next video.